So now let us see on how we can be able to analyze the elastic corrosion in actually one dimension as well as the two dimension. So now let's say we have the object. Let's say this is the object of, let's say, a mass 1, and it is moving towards this direction with initial velocity given as u1, and let's say ahead of it there is an object, let's say object 2, and also it is moving in the same direction with initial velocity given as u2. And of course, it can also be happens that it can move towards the opposite direction based on the nature of the collision. So now, let's say upon reaching at some point, and assuming that the object 1 is moving faster than the object 2, then let's say upon reaching at this point, now the object 1 collided with the object 2, and let's say the object 1 upon actually collided with the object 2, object 1 is having a new velocity given as, let's say, v1, and assuming that the object 2 is also moving with another velocity, let's say velocity given as v2. So now, according to the principle behind the energy, actually behind the momentum conservation, so now momentum before collision, it is the same as the momentum after collision. So in this case, actually object 1 will have the initial momentum given as actually b1 I, corresponding to the initial momentum for object 1, and the plus b2I, corresponding to the initial momentum for object 2, and which is the same as actually b1 final, that is the initial momentum, should be a final momentum for object 1, and plus that should be b2 final, that is the final momentum for object 2. In all cases, actually, in all cases, momentum is said to be conserved. So now, on the same case, it means we'll have m1 u1 plus m2 u2, which is equal to m1, and that should be v1, and that plus m2 should be v2. This will be the formula for the actually elastic collision, and basically whenever both objects are moving before they collide. Otherwise, if one object is said to be at rest, then it means the object 2 will not be there in the initial momentum. So which means whenever one object is at rest, let's say if object 2 is at rest, it means it can have no initial velocity. It could be zero, and actually it could be zero initial velocity. Hence, actually it could not be appear in the formula, which means the initial momentum could only be contributed by the object which is in a motion. And likewise, this actually expression couldn't also be there. So which means whenever one object is at rest, now this is the formula for the actually, this is the formula for the elastic corrosion, that is conservation of momentum formula. Whenever one object is actually at rest before collision. So it can be this. But whenever both are actually moving, it means whenever both are actually moving, It means this is the formula you should know. So keep that in mind. Now, how about the energy conservation? You should have to understand that the elastic corrosion, it actually obeys the energy conservation theorem. At the end of the day, the kinetic energy is said to be conserved. The kinetic energy before corrosion, it is the same as the kinetic energy after a corrosion. Hence, the energy is said to be conserved. In this case, it means we have initial kinetic energy, and for the actually object 1, and plus initial kinetic energy, and for the object 2, which is equal to final kinetic energy for the object 1 plus the final kinetic energy, and that should be for object 2. Now, which is the same as, we'll have it as half mu2, actually mu1 square plus half mu2 square, which is equal to half mv1 square plus half mv2 square. So this is the formula for the energy conservation. And for the case where we have both objects are moving before they collide elastically. Likewise, whenever one object is at rest before actually a collision, it means the other part of the initial the initial kinetic energy will not appear. So will not have this. And for the case where one object is at rest before they collide, so which means we'll just have this. This will be the formula for the energy conservation, and whenever one object is at rest before they collide. So keep that in mind. So now, let's say if we have the elastic corrosion in a 2-dimension. But what is it about if we're saying the elastic corrosion 2-dimension? It means it can be that the objects are moving in a different directions, and they collide, they also move in different directions as well. If we're saying the different direction, meaning they are in different axes, it can be along x-axis and the other one along y-axis, in that case. Now let's say we have object m1, and assuming that it is moving towards this direction. Let's say with initial velocity given as u1, and let's say there is an object, let's say of mass 2, and are moving towards the same direction. It should be towards this direction. Let's say with initial velocity given as u2. So now, assuming that upon reaching at some point, let's say this is the point, the two objects collided elastically, where the other object happens, let's say, to go for this direction. Let's say this is object 1, and having the new velocity given as, let's say, v1, and let's say object 2 happens to go like this with a new velocity, let's say with a new velocity given as, let's say, and that should be given as, let's say, should be v2. So now, at the point in which the objects collided, we can be able to depict the actually two actually the Cartesian plane, where this is x-axis and where this is the y-axis. Let's say this is the case. This is the y-axis, and we can have it in the same way like that, and also have it in the same way like that. Let's say this is the case. So you can see that we have now two-dimension coordinate system, where this is the y-axis and this is the x-axis, in that way. So now, which means the object actually of mass m1 is said to be moving horizontally before collision, and after a collision it can be said that it is moving at an angle, let's say a theta, should be a theta 1 after a collision. Let's say this is the case, and our object of mass 2, we can say it as it is moving at an angle theta 2, actually should be theta 1, let's say should be given as theta 2 before it collide with object 1, and after collision it is at an angle of, let's say, a theta 3 against the x-axis. Let's say that's the case. Of course it can be against this angle, whichever the case, and even after collision can be against y-axis based on the nature of the problem. But this is a typical template, or just have to see what is it about. But the analysis may differ in terms of the angle in which the object is moving with respect to. It can be that object 2 will have to move with respect to x, actually y-axis, like that. It can also be that after collision object 1 can have at an angle with respect to y-axis in that way. So this is a typical template on how you should have to expect whenever the objects are gliding elastically in 2 dimension. So it depends on the nature of the problem that you're having, but this is true for all aspects and are based on the given problem. So keep that in mind. So the skill that is needed is how to analyze the actual vectors in terms of the components, because that is the very prominent idea in the analysis of the actually a dimension in 2 dimensions. Actually the analysis of the momentum should be a collision in a 2 dimension. So keep that in mind. So now we should have to understand that at the end of the day the momentum is said to be conserved. You should have to understand that the initial momentum, it is the same as the final momentum in that case. Now since the collision is in 2 dimensions, which means whatever the case, the momentum along x-axis, initial momentum along x-axis, it is the same as the final momentum along x-axis. So which means you should have to understand that we'll have the initial momentum along x, that will be equal to the final momentum along x as well. On the same case, we'll also have the final initial momentum along y, that will be the same as the final. We'll have the initial momentum along y, that will be the same as the final momentum along y as well. Now whenever the collision is in 2 dimensions, you should have to think about these 2 actually expressions. Should be 2 formulas. So let's start with the momentum along x-axis. Should be the momentum conservation along x-axis. What would be that? So now in this case, since this is elastic corrosion, first thing you should have to present the formula for the elastic corrosion. So the formula says that we'll have it as, now should be should be P1 initial in the plus P2 initial, meaning initial momentum for object 1 and plus the initial momentum for object 2, that will be equal to PF1, meaning should be PF1 or should be P1F. That is the final momentum for object 1 and plus the final momentum for object 2. And now, since the collision is in 2 dimensions, then we'll have to split this into components, that is x as well as the y. So which means we'll have the initial momentum for object 1 along x-axis plus initial momentum for object 2 along x-axis. That will be equal to the final momentum for object 1 along x-axis and plus the final momentum for object 2 along x-axis. And on the same case, in this case, let's think of analyzing what is happening. Object 1, it is along x-axis, so which means the initial momentum along x-axis, it is just been given as the product of mass and its velocity. So we'll have it as m1 u1. And now for object 2, initial momentum along x-axis will be obtained upon resolving this into components. So in this case, let's think of having the Lagrange triangle and see how best you can be able to resolve that. So in this case, this is the this is the y component, that is P2 I y, and this will be given as P2 ix, meaning initial momentum for object 2 in x-axis. So we should have to resolve that into components, so which means we'll have it as m2 u2, and that should be cos theta 2, because this is the component we are looking for and that corresponds to this. Then which is equal to the final momentum for object 1 along x-axis. What will be that? So now this is the object 1 after the collision, so which means we'll have to resolve it into components. So which means we should have this, where this is Lagrange triangle of our interest. So this is how it is going, like that. Let me present it properly. Now this is how it will be going. Now we'll go like this, and also go like this, where this is the x component and this is the y component. So x component, it is going towards the positive direction, so which means we'll have it as a positive. So what will be that? We'll have it as m1 v1, and that should be cos theta 1, and we'll go for P2 fx, that is the final momentum along x for object 2. So which means we'll have to resolve this into components as well. So what will be that? This is the typical Lagrange triangle of our interest. We can be able to have it there. So that is, and that is. So where this is the x component and this is the y component of that case. So which means we'll have to resolve that into components, and of which the x component, it is going towards the positive direction. that is the direction, and we'll have it as a plus, and that will be given as m2 v2 cos theta 3. So that will be the formula for the actually momentum along x-axis. So let's think of having the actually conservation of momentum along y-axis. So let's go for y. Now principle remains the same. We'll have b we'll have b1 iy plus b2 iy is equal to b1 fy plus b2 fy. So that is the initial momentum for object 1 along y-axis, the initial momentum for object 2 along y, and likewise the final along y and the final along y for object 2. So keep that in mind. So now let's go back and analyze the system. Now since the object 1 is actually along x-axis only, then it has no component of the momentum along actually y, so which means we'll have it as L. That will be given as L. Then for object 2, we'll have this component along y, that will be given as a plus because it is going towards the positive direction. We'll have it as m2 u2 sin theta 2. That will be equal to, now the final momentum along y for object 1, it is going downwards, it is a negative, hence we'll have negative m1 v1 should be sin theta 1, and likewise the final momentum along y for object 2, it is this one going towards the positive direction. We'll have it as should be m2 v2 sin theta 3. So which means this is the formula we should have to use in along y-axis, that is the momentum along y-axis, the momentum conservation along y-axis. In this case, what it means is this: along x-axis we had it as m1 u1 plus m2 u2. Let me have it proper here. Then now I can be able to remove all this. So along x-axis we have the momentum conservation as m1 u1 plus m2 u2 cos theta 2, which is equal to m1 v1. But let me ensure that now we should have it as m1 u1 plus m2 u2 cos theta 2, and which is equal to m1 v1 cos theta 1, and plus m2 v2, and of course we should have cos theta 3. So this is for the actual momentum along x. And back to y, which is this, and we'll have it as m2 u2 sin theta, let's say 2. That will be equal to negative m1 v1 sin theta 1 in the plus, we'll have it as m2 v2 sin theta 3. So this will be the formulas that we should have to use in the actually analysis. So in this case, we can be able to solve for whatever we are told to have upon having this. So keep that in mind. Let's say we have this kind of a system. Let's say we have in this case the object of mass 1 and moving towards this direction with initial velocity given as u1. And let's say we have another object. Let me have them properly here. Let's say we have another object, let's say of mass 2 and going towards this direction. Let's say going towards this direction. And let's say with initial velocity given as u2. And assuming that upon reaching some point here, the objects collided. And let's say the other one go like this. Let's say this is object of mass 1 and the object of mass 2, let's say, happens to go like this. Let's say this is v1 and let's say this is the v2. So now, how should we be able to analyze this? So now principle remains the same. Let's think of depicting the actually a two-dimensional coordinate system. In that case, we have this as the x and this is the y, like that. So now it means we'll go like this and also go like this. So now as you can see, before collision, object 1 is moving horizontal, and also before collision, object 2 is moving vertical. So which means after collision, object 2 is having the direction which is, let's say, angle theta 2, and let's say after collision the object 2 is having, let's say, angle theta 1 after collision. And of course can be with respect to y-axis, or let's say for this case with respect to y-axis as well, based on the nature of the problem. So this is just a template where you can just have to see how to analyze the cases here. So now let's start with analysis along x-axis, that is the momentum along x-axis. So along x-axis, initial momentum, it is only for object of mass 1, and it happens to be only along x-axis, so which means we'll have it as m1 u1 and which is equal to, let me have it here, now which is equal to, then we'll have to resolve this into components and also this into components as well. Now the x component for this one, it is going towards the positive direction as you can resolve this, so which means we'll have it as m1 v1 cos theta 2 should be theta 1, and the x component for this actually object, for this object, it is also going towards the positive direction, so it will be positive m2 v2 cos of theta 2. Now this is the conservation, this is the momentum conservation along x-axis. And how about the along y-axis? So now along y-axis, we will only have this momentum before collision because this one is moving along x-axis only. So have it as m, let's say 2 u2 which is equal to. Now we'll have the y component for this one, which is going towards the negative direction downwards. So which means we'll have it as negative m2 v2 sine theta 2. And I also have the y component for this one, which is going towards the positive direction, which is upwards. So which means we'll have it as a plus m1 v1 sin theta. So these will be the formulas, and for the momentum along x as well as the y. Then you can be able to solve for whatever you are taught to with these formulas. How about if we have this system? How about if we have this kind of a system? What if we have, let's say, a case where one object is no longer moving? Let's say we have object 1 of mass 1 moving like that. Let's say with initial velocity given as u. And we have the other object which is at least, let's say, object of mass 2. So now upon reaching, actually after some time, upon reaching this far, object 1 hit the object 2, and let's say they both actually go in different directions. In this case, let's say the object of a mass 1 goes like that, and let's say the object of mass 2 goes like that after collision. So now how should you have that an up to? Now principle remains the same. Let's think of depicting the two-dimension coordinate system in the case. So which means we can have it as this. So where this is the x axis and this is the y axis, you should know. Then let's say after collision, this is angle theta 1 for object 1, and let's say this is angle theta 2 for object 2. Let's say now the angle is with respect to the y axis, and let me also have it, let's say, the angle being with respect to, let's say, y axis in that case. So now principle remains the same. At the end of the day, we should have to look at what is the initial momentum and what is the final momentum along x as well. Actually, what is the momentum conservation along x and also along y, since this is actually a two-dimension collision. So now initially the object 1 is only which is moving, and also it is moving vertically, should be horizontally along x-axis. Now the initial momentum along x, it is only for the object 1 which is also moving along x-axis only. We'll have it as m1 u1, and which is equal to. Now we'll have to resolve this into components and also this into components. And that will go up like this. So this is y and this is x. So now since the angle is against the y-axis, you see that the momentum along x-axis, final momentum along x-axis, and that is for object 1. Let me label it given as v1, and this is given as, should be v2. So which means we'll have it as m1 v1, we'll have it as sine theta 1, because the angle of the collision, it is with respect to the y-axis. We are using the trigonometric ratios. or have the x component that will be in terms of a sine theta. And we'll go for this where I also have to resolve these two components. So which means this is the x component we're looking for, and it is going towards the positive direction. We'll have it as m2 v2, that should be sine theta 2. So this will be the formula along x-axis for the momentum conservation. And how about along y-axis? Initially along y will not have the momentum because this object is moving along x-axis only, and where this one is at rest. Then we'll only have the final momentum along y. That will be given upon resolving. That one will have it as m1 v1 cos theta, and the y component for this, it is going towards the negative downwards. So have negative m2 v2 cos theta 2. So these will be the formulas that I'm going to use in order to solve for anything that we are being told to based on the case of the problem. So take note of that. So at your own time, try to come up with the analysis that will help you to come up with everything you may be asked to upon having the formulas. Let's say we have this case where this is the object of mass 1 and we have the object of mass 2, and assuming that both are going like this. Let's say this is u1 and let's say this is now should be u2, this is u1. Upon reaching here, the objects collided. Let's say this is the case. Now let's say this is the case where object, let's say 1, will have that given as v1 in that case, and let's say the object, let's say 2, will have, let's say of course I should have it as m2, and let's say this is the m1 as well, with a v2 going over in that way. That is v2. So now, can you come up with the two equations for the momentum along x as well as y for this case, assuming that this one is moving horizontally, where you think of having, let's say, two-dimension coordinate system that way. So try to come up with that at your own time. And also think about this one as well. You may have an interest to, let's say we have, now initially you should have to come up with, let's say, what if the object 1, object of mass 1, before collision, it is moving at an angle of 60 degrees with respect to y-axis, and let's say object 2 is moving at an angle of, let's say, 50 degrees with respect to x-axis. This is y-axis and this is x-axis, and after collision the object 1 is moving at an angle of, let's say, 20 degrees with respect to y-axis, and also object, let's say, 2 is moving, let's say, along x-axis. Come up with the diagram of the system and come up with the equations along x as well as the y for the midterms. Let's say we have the system where object of mass 1, it is moving vertically, that is along y, downwards. And the object 2, let's say, is moving along x-axis but towards the left. And let's say after collision, object 1 is, let's say, moving at an angle of, let's say, 51 degrees with respect to the x-axis. And let's say after collision, object 2 is moving at an angle of, let's say, 60 degrees with respect to y-axis. Come up with a system and come up with equations actually for the midterm along x as well as the y-axis. So that's how you have to understand about the collision, elastic collision in 1 dimension as well as the 2 dimension. Thank you. If you have found my videos being interesting and helpful, please don't forget to subscribe to my YouTube channels and let me hear some sort of ideas on how I can be able to have everything based on my contents in the comment sections below. Thank you.